interested for my part. Right, okay. Let's see now for what would be in our eigenvalue eigenvectors. So in our eigenvalue until 8.1.3 will be here. Okay, so we are only going to test you for this quiz up to 8.1, 0.1, 1.2, 1.3. In the exam, it is of course everything, right? Now, today I would do 8.1.1 and 8.1.2, maybe up to 8.1.3, depending on how much time we have. But we'll take it slow, so because we are ahead of the curve. And I'm just going to do overviews. And in fact, this whole chapter came from Lei's book, and you see that we are doing most of the these sections here. And so we're going to start. I mean, and I'm going to motivate first, okay, guys? And how I'm going to motivate is this: there are very uh, very good videos out there, and I'm going to show you some videos, and I'm going to talk through the videos. But let's begin in what I want to say first. All right. So the first idea of eigenvalue and vector is I have A x equals to lambda x. And okay, I'm going to try simple one first, all right? Later on, you realize that the scalar can be even complex. The x can be complex. But let's just do this, the simple thing first. And I'm going to say that a matrix A times a vector x is equals to a scaled version. So this is a scaled version, right? Because all I'm doing is I'm multiplying the original x by a scalar. And you say, what's so exciting about this ax equals to lambda x? And the answer is that if, and we're interested in for x not equals to the zero vector, okay? Because if it's a zero vector, A times any zero vector will qualify, right? Will be some numbers times the zero vector. So we're not interested in the zero vector. But lambda can be the zero scalar. Okay? So some students become confused, right? And think that lambda also must be non-zero. No, it's not. And what's so exciting about this? So the first question to you is, please participate, all right, guys? Since there's only like 68 of you. What kind of matrix is A if this equation needs to be satisfied? Square. Yeah, because if the vector in the input, right? This is the input vector, and this is the output vector. The input vector and output vector must be the same size, right? If it is Rn, input is Rn, output must be Rn in this X. So therefore, this guy must be square and of size n by n. So so for every eigenvalue eigenvector problem, A must be square. So this is the first condition. All right. Now, mm, let's then examine what is AX, guys. So let's examine now the second thing. What in the world is A times X means? And I'll draw you a picture. This is A, this is X, and this is AX. So this picture is nicer. Sometimes you don't like to draw this picture and you abstract it even more and you say, this is some transformation T. And this transformation T is nothing but A times X. Okay? And of course, then this is a linear transformation. Now, I'm going to, to do a simple X first. So the X I'm interested in is belong to R2. All the X belong to R2. So let's call this X1 and call this X2. Therefore, X is X1 and X2. Right. And therefore, any element here, here, anywhere, right, along this grid. In fact, because it's real, it can be anywhere. Is a possible input, right? X belong to R2 means X can live anywhere on this R2 plane. And where is Y? I'm going to draw Y on this R2 plane as well. Now, I'm going to ask you to think what will happen when some A, yeah? I'll give you a very simple A just so that we can understand. 2, 0, 0, 2 is my A, just for example. So I'm going to erase all these other guys now. And then I'm going to just put one value here first. So this is 1, 1, the input. What is my output, guys? If my input X is 1, 1, so this is 1 and this is 1. My output would be 2, 2. Where's 2, 2? Here. So now if my input is 1, 0, my output is 2, 0. And so on. And you can fill up all the red squares and the blue squares, and then you'll realize that a transformation is nothing but moving these dots as the input to the blue as the output. Now, this is interesting. What will happen when my X is 0, 0? Then the output is still 0, 0. So the only dot that might not be moving around is the origin. Okay, for all A. Now, so I'm going to now use this Z star. All right. So he's drawing the same as I'm doing. He's drawing the real line. Sorry, not he's drawing the x1, he's drawing the x2, and this is his A. Okay, I'm going to play, and as I play, I'm going to stop, and then I'll explain. Otherwise, it's Zach teaching you, right? But Zach is a cool guy, right? Zach got 1.35 million and got 34,000 thumbs up for this.
And multiply it by a vector, let's say 1 comma 0, that can
All right, can you all hear his audio? Can someone tell me, please? Yes, great.
be written as such, you'll get out a new vector, or -1 comma -2 in this case.
Right. The blue line is 1, 0, right? 1, 0. And the output is -1, -2. Let's get it out. How do we know it quickly, right? 1 times the first column plus 0 times the second column. So first column is -1, -2. So it's -1, -2. All right, that's how I think. Huh? So this is, we want to do like this guy, -1 times 1, 4 times 0 is -1. -2 times 1, 5 times 0 is -2. This is brute force matrix vector multiplication. It has very little insight, okay, in transformation. Instead, well, I shouldn't say that, but in this example, it's clearer to think of it as 1 times the first column plus 0 times the second column. So since it's 0 times the second column, I can ignore the second column. Minus 1, minus 2 out pops. I don't even need to calculate. That's how I think. All right. So you see that this is the input point part, and this is the output point part. Minus 1, minus 2.
Instead of representing vectors with arrows though, I'll just be using points, which will represent the end of the vector. I'm using Desmos, so it's just easier this way. But still, we have an input and output vector, and you'll notice that the matrix transformation caused the vector to scale and also rotate.
Right, this is the cool part. So he's teaching you that actually matrix vector multiplication is a transformation. Okay, it's transformed by scaling and rotation. And interestingly, he put the center there, and that center thing never move. Okay, so it is really a scaling and a rotation. And this is why it's called linear transformation.
That's usually what happens. Put a random vector in here, and the output vector will likely have a different length and angle. In fact, I'll put a bunch of random input vectors on the screen.
Okay, now he's going to show you that, hey, my x in, okay, x in, y in can be any of these points now. Of course, because we just want to show you as points. Of course, he can be any point between 1 and 2 as well. He's a real line, right? He's a real value. We're just putting points because it's easier for our eyes. All right, so x in and y in can belong to any real value here. So he color coded the input as this orange thing.
Really dots that represent their ends, and I'll apply the same matrix multiplication to all of them at once.
Cool, huh? So, okay lah. I mean, he didn't do it in two colors like I did. 3 blue and 1 brown did that, so you should watch that as well. But basically is he's showing you that when the A matrix operates on each of these points, the point is rotating and moving.
These are the new output vectors, and most of them are just scaled and rotated versions of their associated inputs.
Except the origin. Origin never move. Okay, that's the important point. The origin never move because a times 0 will always be 0. So the origin must not move, and everyone else is moving, rotating, and scaling.
But real quick, if we rewind,
Then he's going to tell you, hey, look at all the points, but some points don't move, don't rotate. That's actually, he's going to tell you it doesn't rotate.
you'll see that any point on these two lines does not get rotated.
All right, he's saying that along these 2 points, they don't rotate. They can grow. They can become bigger, fatter, longer, or shorter. They can be scaled, but they cannot move its direction. The direction doesn't change, or basically, in other words, it does not rotate.
Vectors on these lines only get scaled.
See? So this along this line, he's getting scaled. How about along this line? Along this line, he's not even being scaled, I think. Right? So he's showing you two different possibilities. There's a scaling, here is growing, and here is scaling by 1, which is okay lah, fine. Still scaling, right?
And when a matrix only scales vectors along some line, that is known as an eigenvector of the matrix.
Right. So now you know what is an eigenvector. An eigenvector is simply a vector, whether it's pointing here or pointing backwards, right? Minus. Or whether it's 2 times or 3 times, it doesn't matter. Only the direction is important. So when you put an eigenvector in here, out comes the same eigenvector direction, but scale. Of course, it can be scaled by 1. Let's listen to him again.
Does not get rotated. Vectors on these lines only get scaled. And when a matrix only scales vectors along some line, that is known as an eigenvector of the matrix. The scale factor, or how much larger the vector gets, is known as the eigenvalue.
Right. So in this one, that guy didn't even move, right? So okay, fine. So any vectors along this direction multiplying by the input A, sorry, multiplying by the matrix A does not change its direction. That's an eigenvector. And when it, although it doesn't change its direction, it can be scaled. But in this example, it's scaled by 1. So it's showing you there are possibilities that scaled by 1. In the other line, these vectors are being moved outwards. They are being scaled by 3. So I mean, you see, in 1 minute 33 seconds, you have already tell you what eigenvectors and eigenvalues are. Okay, so Z star is pretty cool.
You'll notice one of these eigenvalues is 1 because when we apply the transformation, those vectors didn't change in length. If you want to rewind it again, you'll see the dots on the other eigenvector all got 3 times as far from the origin. Now if I change the 2 by 2 matrix to this, aka a rotation matrix, then any input will be rotated 90 degrees.
Huh. So now he's telling you, all right, I'm going to change the matrix into this value, and this is a rotation, right? 90 degrees rotation. Any vectors along here will be rotated by 90 degrees. Any vector along here will be rotated. So it means that in this very interesting example, that no vectors stay still except the 0 element, the 0 vector. All right?
So the question is, what is the eigenvector of this new matrix?
Right. Uh, I mean, if we have a chance, we'll deal with this, and the complex numbers will come out. Okay, the complex numbers, the eigenvalues will be complex numbers, and eigenvectors as well.
And by the way, 0, 0 doesn't count. Well, considering an eigenvector is a vector not rotated by the matrix, we can say that an eigenvector doesn't exist here, because every vector besides 0, 0 gets rotated.
Yeah, but so if we are restricting our input, sorry, our whole operations to real numbers, yes, he's right. But if because you already have studied complex numbers, so there are such things as complex eigenvectors and eigenvalues.
When you go through with the analysis though, you do come out with eigenvectors and eigenvalues. However, they're imaginary. There isn't as much
Yeah, see? So eigenvectors and eigenvalues can be imaginary. Cool, huh? Anyway, so that is Z star, I think. All right. So that's Z star. I'm done with Z star now. And the other guy I want to show you is our friend 3 blue 1 brown. So 3 blue 1 brown is even more cool than Z star, right? He got 6 million subscriber with 97K just for this video alone, the eigenvalue, and he took 17 minutes. So you should watch this guy. I mean, Z stars one, you can watch the first part. The later part becomes much more complex out of the scope of this. But this 3 blue 1 brown one, no problem. You can watch the whole 17 minutes and you'll be able to do one small problem of our linear algebra. All right, so let's begin with him now. And I'm just taking this very slow so that we drum this to death and we'll see how far we can go with this.
If you have a solid visual understanding, and I think most books do a fine job explaining it.
And basically, he's telling you that eigenvalues and eigenvectors are not so difficult, which is true. I mean, later on, you'll see that we are only playing with 2 by 2, 3 by 3 matrices, and we are finding the eigenvalues and eigenvectors of things.
The issue is that it only really makes sense if you have a solid visual understanding for many of the topics that precede it. Most important here is that you know how to think about matrices as linear transformations. But
Yeah, so he says that to understand our friend, the eigenvalue, eigenvectors, you definitely have to understand what is linear transformation, which is AX. So now you know that AX is nothing but moving the points around the R2 space if your input is R2. And determinant, later on you realize that we need determinant to get something done and system for equations to solve. All right, well, let's begin. Okay, again the same thing, but 3 blue 1 more is even more cool than Z.
eigenvectors and eigenvalues themselves. To start, consider some linear transformation in 2 dimensions, like
Again, again he shows the gray line as the input. and the green is 1, 0, and the red is 0, 1, the two standard bases of R2. He called this I hat and called this J hat. And now he's showing you that when I fire my AX, AX is going to operate on this grid. Then the two things is going to move. Why is he only interested in these two guys? Why not the rest? Actually, if you know how these two bases move, you know how every other point move. Okay, then in fact, linear algebra is all about playing with the basis.
Some linear transformation in two dimensions, like the one shown here. It moves the basis vector I hat to the coordinates 3, 0, and j hat to 1, 2.
All right, guys. So I'm going to pause and I'm going to ask you this question. What is my A in this example that he have just shown me? He moved. Okay, I'll play it again. He moved the green, which was from 1, 0 to 3, 0. So he basically says, I'm going to move 1, 0 to who? To 3, 0. Right? So I haven't tell you what A is yet, but I told you that I'm going to move from 1, 0 and I will land in 3, 0. What operations here on my left, A, can make this happen, guys? Right? That's the picture he showed you, right? My input is 1, 0. Ignore the red guy first.
Dimensions, like the one shown here.
And out comes 3, 0. So what is A? Anybody? What values must I put in A such that this will happen? 3, 0. Yes. And how you think, how you think, very good, guys. Thank you. Keep it coming. How you think is this? It is this little guy here, this guy, times this guy is the only interesting possibility, right? Because this guy, 0, is multiplying with this column. So only this is interesting. And therefore now we can write 3, 0. And that's why we are interested in basis. Can you see now? This is the first. Yeah. We're only interested in what will happen on this. Now let's try the next guy. Here. Here is 0, 1. All right, let's see the picture again. Now let's focus on the red guys now.
Third, consider some linear transformation in two dimensions, like the one shown here.
They move by 1, 2. So now if I'm focusing on if I'm now focusing on 0, 1 and out comes 1, 2, therefore I'm only interested in this column 1, 2 because 0 is going to be multiplied with this guy. So he has no effect whatsoever. 1 is going to be multiplied with second column, 1, 2. So the matrix A is this guy, 3, 1, 0, 2.
It moves the basis vector I hat to the coordinates 3, 0, and j hat to 1, 2. So it's represented with a matrix whose columns are 3, 0, and 1, 2. Focus in on what it does to one particular vector.
All right, now he's going to take some random vector here. And guys, what do you think will happen? Okay, let's have a conversation. What do you think will happen? Of course, you can think of this number as 1.5 and maybe 0.75, and then you can plug it in, right? But he's not going to do that. He's going to just punch this A multiplied by the yellow vector, and he's going to see it move. And we for sure know that it's going to be scaled and rotated.
And think about the span of that vector.
Right? He's now trying to tell you the idea that if this vector, if I give you this yellow vector and a scaled version of this yellow vector means that he's going to live in this span, right? That's the word span, the spanning set, the 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 span of the basis. The word span means the linear combination. Here, there's no linear combination. There's only one. But actually, the word linear combination has two interpretations. It's the scale, and add. Right here, we are going to scale. Okay, that's we are going to scale the yellow vector. So this pink line here is the span of this yellow vector. Means that if I multiply by 2, you'll grow. Multiply by 3, you'll grow. If I multiply by -1, you'll grow the other opposite way. So this is a span. Now the question is, would the yellow vector move on the span or move out of the span?
The line passing through its origin and its tip. Most vectors are going to get knocked off their span during the transformation. I mean, it would seem pretty coincidental if the place where the vector landed also happened to be somewhere on that line.
So basically he says that normally all the vectors we give to you, I mean, after you transform AX, you'll get out of the span. However, like, because we're learning eigenvectors today, we realize that there are very special vectors with certain directions that doesn't get knocked off the span.
But some special vectors do remain on their own span.
1 minus 1. I mean, he's using 1 minus 1. Huh? But actually, he could have used minus 1, 1 as well. He could even use 2, 2. 2 minus 2. So all these are eigenvectors, but he just chose the simplest one. 1 minus 1. And then he's going to multiply by this. And then look what happened.
Meaning the effect that the matrix has on such a vector is just to stretch it or squish it, like a scalar.
So now he demonstrated A times 1 minus 1 becomes 2 minus 2. Okay? So let's be very pedantic about this. Oops. All right. A is equals to 3012. And I'm going to multiply by who? 1 minus 1. So this is AX. And now output is, it is first column 30. So this is how I deal with it on 30 plus minus 1 times the second column, 1, 2. This is how I think actually. I don't do this row times this guy. All right, I do it. I think of it as first column times 1 plus minus 1 times the second column. And the answer is 3 minus 1 is 2 minus 2. So 1 minus 1, 2 minus 2, isn't this 2 times the original 1 minus 1? This was my x. Oh, okay. So now I see that it's fine. But let's plug in another value, guys. Let's do this to death so that we'll never have this question again. How about minus 2 times this guy, which is minus 2 plus 1, right? So it's minus 2 times the first column plus 1 times the second column. And what do I get? Minus 6 plus 1 minus 6 plus 1. Did I make a mistake, guys? Minus 2 minus 6 minus 6 plus 1. I made a mistake again. Minus 2. Oh, yeah, yeah, yeah. Yeah, where's minus two? That's why. That's, yeah. Like I say, I'm dyslexic, huh? Thank you, guys. So when I make this kind of mistake, please forgive me. Minus 6 plus 2 is minus 4. I knew something was wrong when I couldn't match up. Minus, okay, here's 0 and here's 2. And isn't this, again, 2 times minus 2, 4? My original, see? Okay, so it is always a scalar. So see? So these are eigenvectors. Eigenvectors is not a single vector. Eigenvector is any guy along this yellow vector. Up, down, scale, doesn't matter. All right? Eigenvectors. Eigenvalues don't change. Any guy along anyone, he's an eigenvector, he'll be scaled by the corresponding eigenvalue.
For this specific example, the basis vector I hat is one such special vector. The span of I hat is the x-axis.
He's telling you that in in this example, what I had is going to be scaled by 3. This is obvious. Immediately it's obvious. The other guy wasn't so obvious, but 3, 0 was obvious.
And from the first column of the matrix, we can see that I hat moves over to 3 times itself, still on that x-axis. What's more, because of the way linear transformations work, any other vector on the x-axis is also just stretched by a factor of 3, and hence remains on its own span.
All right. So, guys, I mean, I took a long time to show you what the eigenvector and eigenvalue is, right? So, is it clear now? Anybody have any questions whatsoever? So, in fact, this is a what do you call it? A very slow version of. But the previous video says the eigenvector will only be the two positive lines. What do you mean, Jiahui? Okay. The previous video, Zach's video? Yes. No, 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 no. What they are saying is this. Okay, let me fast forward. Okay, he's showing you the two eigenvectors. One is here and one is here.
Is negative 1, 1. It ends up getting stretched.
See? Can you see? This guy doesn't move out. This guy doesn't move out. So these two are the eigenvectors in this matrix. Different matrix have different eigenvectors. Okay?
A slightly sneakier vector that remains on its own span during this transformation is negative 1, 1. It ends up getting stretched by a factor of 2. And again, linearity is going to imply that any other vector on the diagonal line spanned by this guy is just going to get stretched out by a factor of 2.
So this was what I give you, right? He gave you 1 minus 1 and it's stretch. I give you minus 2, 2, it also stretch. So any vectors along this yellow is an eigenvector. That's what he means. Any vector along this green is an eigenvector because he doesn't get out of the span. Okay, so this is what we're talking about. All right. So now, okay. Now I'm going to use MATLAB to show you how is it done so that you guys can use MATLAB as a tool. So please, we are not testing you MATLAB for sure, but we are saying you if you can. I mean, you use ChatGPT, you use Google, and you use some graphics calculator. Now you can use MATLAB. That's it. MATLAB is a tool. That's it. All right. Let's punch A in. A is equals to 3102. So that's the. So I'm going to write it here so that you guys can see it as well. So A equals to 3102. And then ED equals to EIGA. All right, so the notations or the commands, EIG is eigen decomposition. Then the input is a matrix square, and the output is two things. This is the diagonal matrix containing the eigenvalues, and this guy is the corresponding eigenvectors. And he will look like this. You call this E1, E2. Eigenvalue 1, eigenvector 1. Should I use E? Let's not use E. Let's use E. And this is D1, D2. For a 2 by 2A, remember that when we play with eigenvalue and eigenvectors, we are saying that if we submit A by E1, what is the thing that I'm going to get? Something by E1, right? And then is D1 by E1. So this guy is the eigenvalue. If we submit A by E2, A matrix multiplied by E2, we'll get the scalar D2 by E2. Oops. All right, so now you know that the 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 MATLAB just simply give us a nice calling function to play with this. Let's see, okay? E stand for eigenvector, D stand for the diagonal eigenvalues, A. And out comes his thing. Okay. So E is equals to 1, 0. And minus 0 0.707, 0 0.707. E 3, 0, 0, 2. So it means that our friend here has the eigenvalue 3, and the other friend here has the eigenvalue 2. Why did he choose minus 0 0.7, 0 0.7? Where is that? Let's draw. Who is minus 0 0.7, 0 0.7? Is this guy. This is, oops, minus 0 0.7. Oh, wrong guy. Ooh. Minus 0 0.7. I should be going left first. And then up. So he's this guy. So he's this guy. He's this vector. Who is 1, 0? Let me draw in blue. This is 1, 0. So isn't this blue and this red exactly the same as what he was drawing just now? Right? So let's go and see our friend. See? Same, right, guys? The yellow is minus 0 0.7. But inside he's drawn as minus 1, 1. But we already told you, it doesn't matter the length of this yellow vector I give you, as long as the direction is correct. So what did our friend MATLAB do? He normalized the vector to unit length 1, and this is unit length 1. So the green, in fact, is 1, 0 here. So far, okay, guys? Any problem? So given the matrix, it finds all the eigenvectors for that matrix. Yes, if it is able to. Very good, outstanding. The question is, can MATLAB always find all the eigenvalues and eigenvectors, it will try its best, right? So, I mean, of course, if you have MATLAB, then, in all the tutorial questions, you can do it in one statement. Pop, pop, finish. But so there are some metrics which will say there is no, it cannot be decomposed. Okay, we'll explain to you why now. Mm. Okay, now I'm going to do a different. I'm going to do a different thing. Can I do a different thing? All right. Okay, I'm going to do this now. Something called eigen decomposition. Let's still play with this matrix A. 3, 0, 1, 2. And we have found that when x1 is equals to 1 minus 1, this is an eigenvector, and the corresponding eigenvalue lambda is equals to 2. A x1 equals to 2x1. Right, guys? This guy? Which one? Yeah? What do you need? Yeah? All right. Now, okay. So we knew this. We also got the other guy, x2 and lambda. So you realize that I'm going to introduce notations now. Huh? x1, lambda 1. x2, lambda 2. So they are associated. Huh? This vector is called an eigenvector of lambda 1. This vector is an eigenvector associated with lambda 2. Lambda 2 times x2. Okay, lambda 1 times x1. All right. Now, okay, don't blink, guys. A x1 equals to lambda 1 x1. A x2 lambda 2 x2. So far, okay, yeah? A x1 x1 lambda 1. Then it says there's no magic here, right? Everything is the same. What about these guys? This is 2 by 2. This is 2 by 2. This is... What am I going to write on the right-hand side, guys? Yeah, of course it's 2 by 2. Very nice. But what else? What about this guy? This guy. The first lambda 1. Okay, very nice. Okay, I'm going to write lambda 1 x1 lambda 2 x2 cool, guys. Everyone happy? Nothing great is happening here. A times x1 is lambda 1 x1 lambda 2 x2. Can I write in one more way, guys? Equals to, what do you think I'll write here now? If this is x1 x2, what is the way that I will write here? This is the E matrix, guys. This is the D matrix. Therefore, it is a diagonal matrix. And it will be lambda 1, lambda 2. And now you will see that I'm going to use blue. So now you can see blue. So now I want to do green. I should do green first. What do you just see, guys? Lambda 1 times the first column, right? 0 times the second column. So I get back x1. Ax1, I mean. I get lambda 1 x1. The second, what about this one? 0 times the first column plus lambda 2 times the second column. So if I really color code this properly, this should be lambda 2 x2. And this is lambda 1 x1. Can you all see? Nice, huh? So now you can see A. So in English, it is A. And who is this guy? We call him E, right? And it equals to, who's this guy? E, right? Times D. Now, if, if who is invertible? If E is invertible, then what do you think I'll write? A times E minus 1, E times D, E minus 1. A equals to E D E minus 1. This is called eigen decomposition. Right? Okay, let's play with this. What is our E? Oh my god. E is. So far, any question, guys? Yeah, this is a huge step, huh? Right? I mean, we thought we are playing with just decomposing A into eigenvalues and eigenvectors, and out comes this guy, right? So that's why when we are playing with linear algebra, actually we are just playing with A, B, C, D, E, ML. Yeah, we're just moving it around. All right, E. Who's E? Oh, someone asking me a question. One, yes, Singwei. So sorry I didn't get to see your message until now. Anybody? Singwei? Okay. All right, let's push on. E is 1 minus 1, 1, 0. Who's D? 2, 3. Who's E minus 1? And then if it works, it will outcomes our D, our A, which is 3, 0, 1, 2. Okay, so I'll show you. In fact, I'm lazy, right? So I already have E and D. So it's E times D times inverse of E is equals to A. Can you see? Yeah. Now, my E is 1, 0. This column is 1, 0. But we already told you that eigenvectors, as long as it spans that direction. So I'm going to do this. E is equals to, I'm going to use 3. And here is minus 1, 0, 1. Then you see that this E has nothing to do with this E. Or has it? Guys, please answer the question. This E, the original E given by my MATLAB, and the E that I have just punched in, any relationship. The relationship is How is x1 now related to x1? They are the same direction, different scale, huh? Same direction, different scale. Now, let me ask you. E times D times E inverse. Answer is there. Again, it shows us that eigenvectors, as long as it's pointing in the correct direction, has no effect. We can use any guys. The D must be there. All right? Okay. So we are done. Now, any questions, guys? Anyone? Maybe I should ask you some more things now. Yeah, can y'all type something here and give me 5 minutes? I'll come back. Law 11. Can you tell me anything you want to know? And of course, if you want me to do how to perform eigenvalue and eigenvectors of the 2 by 2, I'll do it in the next 20 minutes. But can y'all type something here, please? Clear so far. Real world you don't want to go there, guys. Real world applications. But all right, I'll tell you some real world applications. Give me 5 minutes. Multiplicity. Okay. Real world applications. I can answer this. All right. What does could lecture means, guys? Easier to grasp than DFT. What does type true means? Okay, let me try. Real world. Okay, you guys want real world? Here's real world. A. How about doing A 1000? Man, yeah, I mean, this is 2 by 2 is still easy. But imagine if it's 10 by 10, 100 by 100, 1000 by 1000. Close to impossible to do any kind of things like this. But remember, what is A? E D E inverse, right? We got E D E inverse. E D E inverse 1,000 times. E D E inverse. Then because we know that it doesn't matter about the brackets, right? What's the thing? It's associative. So we can throw away the brackets. And of course, now you see what happened to all the brackets. All the E inverse, E cancels. And therefore now we are left with, and because all the D's, there's 1,000 of them, the last E inverse, of course, is not cancelled. So I'll show you E D E inverse, E D E inverse. And this is the last guy, the 1,000 guy. And of course, then our these guys cancel. And then now we are all left with D times D times D 1,000 times. And what is D, guys? D is equals to lambda 1, lambda 2, for example, right? And then now, when we want to do D squared, so basically it's the same. And now when we are multiplying, we observe that, and we observe that, and therefore A 1,000, and we can do this easily because diagonal matrix are nice. Okay, so this is called the diagonalization. So where's the diagonalization? Yeah, chapter 5.3. So I've skipped chapter 5.2 because it's not really. I've done chapter 5.1 to death. What is I've done begin to do chapter 5.3. I haven't do 5.2 yet because it's not very exciting. Okay, but and I mean, what is 5.2? 5.2 is your typical, very simple 2 by 2 matrix decomposition questions, which you have to do, of course, because we are always going to ask you to find the eigenvalues and eigenvectors of these guys. It's not very exciting, and I mean, I've given you so many examples, especially Patrick GMT. He's going to give you a matrix, and he's going to show you in a step-by-step form how to do it. Even 3 blue, 1 brown shows it to you. Strength shows it to you. Everybody shows it to you. Man, it's so boring. But 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 you guys have to do this because in the exams, we will give you a 2 by 2 or 3 by 3 matrix, and we're going to ask you to find the eigenvalues and eigenvectors for sure, right? I mean, this is a standard question. It's not very exciting. It's just very mechanical. Okay? But maybe since we have time now, do you guys want to do this? How about that? Can you someone tell me? I mean, time is yours. Or do you want to do something else? Anyone? We have 1 hour. I mean, we've just done 1 hour. Anything else? Or do you want to take a break? No? Are you guys still here, by the way? Thanks. But wait, where are we now? Okay, you guys are still here, right? Sample quiz questions. I can't think off my head. Huh? Okay, I don't know what's happening because I. Mm, all right. Summary. All right, I'm going to summarize for you. I'm going to summarize for you. Let's do. Okay, you guys got to help me. I realize that I'm really bad at numbers. Let's find eigenvalue vector of A equals to 3, 0, 1, 2. The matrix that we are playing with. Okay? And that's always the standard question. Find the eigenvalue, eigenvectors of one square matrix. And we begin with the principle that A, let's call this V now, all right? Eigenvector equals to lambda times eigenvector. And the condition is that V cannot be the zero vector. And the lambda is a scalar. Can be zero. All right. So there's a problem with this equation, guys. What do you think is the problem? Can you see a problem with this equation? It looks very nice, huh? This is a 2 by 2. This is a 2 by 1. This is a scalar 1 by 1. And this is a 2 by 1. So we end up with 2 by 1. So it looks okay. But on the left is a matrix vector. And on the right is a scalar vector. So I cannot combine, right? It's like, hey, still this is a 2 by 1 vector. And then you say I cannot collapse these two, right? I cannot do I cannot combine A and lambda together. There's a V sticking there. So what is lambda V versus lambda IV? I is the 2 by 2. So let's see. Lambda V1, lambda V2. Let's assume that V is equals to V1, V2. V is a two-dimensional vector. Lambda V means I basically bring the lambda inside. Okay, fine. Lambda, what is I? I is 1, 0, 0, 1. What is V? V1, V2. So far okay, guys? What is lambda I? Oops. Lambda 0, 0, lambda. V1, V2. What is this? Again, remember, V1 multiplied by the first column. Lambda V1. Second guy, V2. So it's lambda V2. So now they are the same. So we realize that this form is what we want versus this form. Why? We don't like this way because we cannot combine the two matrices together. So now we have A V minus lambda I V. And now we have A minus lambda I V. We're going somewhere. We have already collapsed these two. So remember, what is the interesting V? If we multiply V as 0, anything times 0 is 0 vector, right? This is a 0 vector. So V must be not equals to 0. Condition, huh? Remember, eigenvectors V must not be 0. What is lambda I? This is lambda I. So now we now know how to play with this. What is A? 3102. 3102. This is A. Minus, what is lambda I? Lambda I is minus lambda 0, 0, lambda. So this is lambda I. Bracket V equals to 0. Okay, we're almost done. So this guy become 3 minus lambda, 1, 0. Let's give him names first. All right, let's give him names. A minus lambda I. He has a name, guys. Let's find his name. Where is it? A minus lambda I. Mm. A minus lambda I. Oh, the determinant of A minus lambda I has a name. Okay? A minus lambda I is just A minus lambda I. Later we're going to find the determinant. All right, let's see. So this is A minus lambda I. So A minus lambda I is equals to this guy minus this guy. 3 minus lambda. 1, 0, 2 minus lambda. So this matrix is the interesting one because this matrix must be what? For V not to be equals to 0, remember this matrix multiplying by V when it's still 0, this matrix must have what? Must have what, guys? Must have? This matrix must have what? Can you all fill in the blanks, please? You're still here? Anybody? Zero determinant. Yes. Must have dependent column. Right? Okay, I'm going to rewrite this. Let's call this B. X equals to 0. X is not equals to 0. Therefore, B must have what? B times X is equals to the 0 vector. Okay, let's call this matrix B. Therefore, B must have dependent column. When B has dependent column, therefore, B what is not invertible. Has 0 as the determinant. Can you see now? And then, of course, all the 10 or 13 properties of the invertible matrix. All right. So now, let's clear this out of the way. Therefore, the determinant of A minus lambda I is equals to 0. Now, this is a huge jump, okay, guys? There's a jump because I will show you where the jumps are. The jumps first is AV equals to lambda V. This is very innocent. The second jump is here. AV minus lambda IV. This is a clever idea where we use the I such that we can cast lambda V as lambda IV so that we can merge this guy to get this equation. Second jump. The third jump is here. We realize that this equation V times V equals to 0 means that this guy has dependent column. But we have two unknowns, right, guys? Look, we have two unknowns. Who's unknown? Here's one unknown. Here's one unknown. We have two unknowns. How do we solve? We couldn't solve. So the clever idea is that, but we know the condition. This guy has dependent column for V not to be equal to, for non-zero V, because right hand side is 0. So the most clever idea was this. I mean, it took me a long time to figure this out when I was a student. Was that, hey, let's cast the problem as this. The determinant must be equal to 0. So what disappear, guys? V disappear. We only need to solve one problem now. Therefore, now we can solve for lambda. And this is the characteristic equation of this uh, eigenvector. See, this determinant must be equals to 0. And remember, in a 2 by 2 case, this is AD minus BC. So, so we're going to now say, oh, I got no more battery for my pen. Yeah, 0%. Okay, give me 2 minutes. So now, you see, we have this determinant equals to 0. This 3 minus lambda times 2 minus lambda minus the other diagonal, multiply. So now, see, we only need to solve for lambda now. V disappears. This is really clever. All right, so the determinant of A minus lambda I is equals to 3 minus lambda, 2 minus lambda minus 1 times 0 is equals to 6 minus 2 lambda minus 3 lambda plus lambda square. And then now we have lambda square minus 5 lambda plus 6. And then right hand side is equals to 0. Right? Now you can factorize this. Lambda minus 3 lambda minus 2. Right? Lambda square minus 3 lambda minus 2 lambda is 5 lambda plus 6. Okay. Therefore, lambda equals to 3, lambda equals to 2 are the eigenvalues of A. So now that we have solved for this, we can take each, let's call this lambda 1, then call this lambda 2, and now we can solve for corresponding, okay, that's the keyword. V1 for lambda 1, V2 for lambda 2. Okay, we are almost home. Last page. So we know Ax equals to which lambda are we going to solve for? Let's solve for lambda 2 first. 2x. See, now, now all right, guys, just let's do it slowly. Lambda 2x. We know that ax2 equals to lambda 2x. We now know what is lambda 2 because when we started, we didn't know lambda 1, lambda 2, x1, x2. But now, with that one little step, we solve for lambda 1, lambda 2. So now it's 2x2. So now we just need to fill in all these guys. 3, 0, 1, 2. Okay, x2 minus, oh, come on, guys, equals to 2I times x2 equals to 2002 times x2 is equals to 3012 minus 2002 times x2. Okay, so this is A minus lambda I times x2. This is the equation we are doing. And now, of course, we have 3 minus 2, which is 1, 0, 0, 0. Oh, I made a mistake again. Where is my mistake, guys? 3. Did I make a mistake? I must have made a mistake somewhere again. Anyone? 1 minus. Yeah, I realized that I make always this mistake. All right. Okay, let's not call this x2 now, guys. Let's just call this little big x. So, so let's call this element 1, 0, 1, 0, and then let's call this x1 and x2. I don't know about you guys, huh, but I always have problems solving this. So, implying x1 is equals to x2. There is a pivot and one free variable. So, x1 equals to pivot, x2 equals to free, right? Then let x2 equals to lambda. Therefore, x1 equals to lambda, x2 equals to lambda. Did I make a mistake again? Oh yeah, minus, minus, right? Yes. Therefore, the vector x is equals to minus lambda, lambda equals to lambda minus 1, 1. Clear? So that's it. I mean, if you're in the exam and you need to do 2 by 2, this is that very few steps that you play with to find the eigenvectors. Once you have the eigenvalue. So let's summarize. So I never like to go through this because it's so boring, but okay, but it's a 3-page problem. The steps to perform this is this. Once you are given A, the first step is always to find the eigenvalues. To find the eigenvalues, we work it out and will generate the characteristic equation and find the determinant of this equation, A minus lambda I. When you solve for this, if it is R2, you have 2 values, 2 roots. If this guy is 3, you have 3 roots. But you could have repeated roots. Okay? So later on you'll see something called algebraic multiplicity and geometric multiplicity. The roots will reveal to you the eigenvalues of this matrix A. For each of these values of the eigenvalues, you're going to substitute and you are solving. What are you solving, guys? This is the interesting part. You're solving to find eigenvectors. And the eigenvectors are what? Are of what? What is this word that I'm looking for? See? I am finding this is A minus lambda I times x2. x2 is the eigenvector. So the eigenvectors are what of this matrix? A minus lambda I. The null space. Excellent. Outstanding. 1 mark for the exam. The null space. Okay? So the null space of this matrix is the eigenvector. So cool, huh? Of course, it must be very clear. The null space of the corresponding eigenvalue, right? Okay, because there are 2 of them and you can go and solve for the second one by yourself. I'm done. Oops. Okay. Now, and I mean, let me just go through the slides. Where are we now? And we're here, right? We're at 8.1.2. And here are the things that I've gone through. And just now I told you about the determinant, right? Yeah. If it is invertible, the columns must form a linearly independent. Therefore, because ours is linearly dependent, therefore it is not invertible. And all the other conditions are, are what related. Okay, what else? I think I'm done with all this. Yeah. Where there? Yeah. Here is what our friend have just told us. The null space of A minus lambda I, which is not equals to 0, we're not interested in the 0 vector, is the eigenvector, right? Okay. Anything else? I think I'm done. Yep, that's it. So with that, we are done and we'll continue again next week. Let me stop sharing now.